This is the Algebra 2 Chapter 7 review. For this first problem, we need to make a rough sketch. Now, what I'm going to do is I'm first going to make my x and my y chart so that we can come up with some points that we can plot onto a coordinate plane. So I'm going to plug in -2, -1, 0, 1, and 2 into this function that they've given me, y equals 4 to the x. When I do that, I'll get some points that I can graph. Now what I'm going to put are the decimals that I get when I do this. When I plug in -2, I get 0.0625. 4 to the -1 is going to give me 0.25. 0 will give me 1. 1 will give me 4. And 2 will give me 16. So then I'm going to create a rough sketch here. Okay, it's going to be a really rough sketch, but I need to graph these 5 points. So -2, 0.0625, that's just going to be really, really close to my x-axis. -1 is going to be a little bit above that. 0, I'm at 1. 1, I'm at 4. And 2, I'm all the way up here at 16. So my graph is going to look something like that. Now again, that's a really rough sketch. Remember that in each graph, though, we're going to have an asymptote. Which is a line that this graph will approach. So it's approaching it right here, but it's never going to touch it, it's never going to cross it. Okay, next problem. An initial population of 175 quail increases at an annual rate of 6%. Write an exponential function to model the quail population. What will the approximate population be after 4 years? Okay, so the first thing I recognize is I'm talking about something increasing at a specific rate. So I need to be thinking about our formulas that we learned. I know we learned one, it was a of t equals a times 1 plus r to the t power. So in this particular problem, I know that 175 is my initial amount. Again, I know that this is going to be a plus sign right here because it's talking about increasing. My rate is 6%, but we need to convert 6% into a decimal, which is 0.06. And then my time. Well, my first part says write an exponential function to model the quail population. Because they told me 4 years, I can put that in when I'm actually calculating. So I've got initial amount times 1 plus 0.06 to the 4th power, and then I'm going to put this whole thing into my calculator. When I put the whole thing into the calculator, it's going to spit out 221. So that's the amount of quails that will be in the population after 4 years. And then this would be like my function that would model this quail population. If I replaced this 4 with just a t, then that would give me any other time that I wanted to plug in as well. Okay, here we are talking about translations of a function. Now remember, when I have you do these problems, what I want you to do first is circle your base and the exponent, because that's like your parent function. So I'm going to do that in both of these next 2 examples. Circling my base and my exponent, just the x. Because now anything outside of that circle I know is going to impact my function in some way. I just have to figure out how. So for number 3, this 1/6. If I am multiplying by a number in the front of my function, that means it's going to be a stretch or a compression. So because this is less than 1, I know this is going to be a compression by a factor of 1/6. So because I am multiplying a number in front, I know it's going to be a stretch or a compression Because this number is less than 1, it is a compression. Now in the next example, I'm still multiplying by a number in front, but this time it's greater than 1. So this is a stretch by a factor of 4. I also have this plus 3 here though. This plus 3 is tacked on to the very, very end of the problem. It's not up here in the exponent. If it were up here in the exponent, then that would mean I'm going left and right. Because it's at the end, I know that this is a shift up and down. I know I'm going to shift up 3 because it is positive, and positive means I'm going up. The next problem I'm just going to put into my calculator. So we have an E button on our calculator. I type in E to 2.2. Be careful, that's 2.2. And my calculator will spit out 9.025. That's it. It's just my calculator. Okay, reading through this next problem. Suppose you invest $900 at an annual interest rate of 3.4%, compounded continuously. That's important. Compounded continuously means I'm going to be using PERT. So my amount after T years is going to be equal to that formula PERT, where P is my principal or my initial investment, R is rate, T is time in years. E is just the letter E, and remember that's a button we can hit in our calculator. So I'm going to plug all of these things in. It told me that I initially invested $900, and the rate that I invested at was 3.4%, which is the decimal 0.034. So I'm going to put that in here, 0.034. My time is 7.5 years. So I'm going to type this entire thing into my calculator. When I do that, it'll tell me that after 7.5 years, my total amount that I have made is $1,161.42. Okay, the next problems are asking us to write an equation in logarithmic form. So remember, for logarithmic form, you are going to take your base, and that becomes the base of your log. So I'm going to have log base 3. Here, my base is 8. So log base 8. And then these two numbers here, the 5, the 243, switch spots. So my 243 comes here. It's equal to 5. Here, my 16 comes here. It's equal to 4/3. All right, now we're evaluating the next two problems. When we evaluate, the first thing we have to do is set these things equal to x, because we're trying to figure out what it is equal to. Now, I'm going to put this equation into logarithmic form. Into exponential form. I have it right now in logarithmic. So I'm going to take the base of my log, and that becomes the base of my exponent. It's going to be 2 to the x equals 128. So now I have to use my brain. I'm going to use my calculator to help me out too. 2 to the what power is going to give me 128? Well, I know that it's not going to be 4 because that's too small. I'm going to try 5. That's not it. I'm going to try 2 to the 6th. Remember, we can do this all in our calculator. And then when I try 2 to the 7th, I see that 2 to the 7th is 128. So x equals 7. Now, in the next problem, remember, if there's not a log base written in, we know that it's 10. So I have 10 to the x equals 0.1. So I'm going from a larger base to a smaller number. Now, when that happens, we need to be thinking about some negative values. So, if I try x equals -1 in my calculator, I'll see that it will give me 0.1. 10 to the -1 power is 0.1. For these next two problems, they want us to take these multiple logarithms and express them as a single logarithm. So I need to squish them together using my properties of logarithms. Okay, so the first thing I see is in this first example, I have some coefficients in front of my logs, which I'm not allowed to have if I'm compressing. So I need to use my power rule to stick them back as exponents onto my argument. Remember, my argument is the thing after the base. Okay, the next thing I have to check is that they have the same base. They do in this case. My base is the letter B, which is different because usually we have a number, but that's okay as long as they're the same. My base is B. Okay, so I've moved my coefficient up into the exponent, and I've also confirmed that I have the same base. Next thing I check. This is addition happening here. And addition means that when I combine these two things together, I need to be multiplying them. So I write my single log base B, and then I'm going to multiply t to the 4th, y to the 6th, and that is your answer. Now in the next problem, I don't have any coefficients, so I don't have to move those. My base is the same, my base is 5, and I see that I have subtraction, which means I'm going to be dividing these two things. So I write my single log base 5, but then I take 100 and divide it by 10. Now, I'm not done yet because we know what this is. 100 divided by 10 is 10, so I'm going to write it one more time. Log base 5, 10 is your answer. Now, in this next problem, we're going the opposite direction. It wants us to expand. So I'm going to take this thing and I'm going to start pulling it apart. Well, the first thing I see is that I have 5 and n squared. Those are two different things, 5 and n squared. So I'm going to break it up. I'm going to take this, I'm going to break it into log base 6 of 5, and addition, because that was multiplication, log base 6 of n squared. Now the last thing I have to do is take this little n squared here and move it down. So I get log base 6 of 5 plus 2 log base 6n. Now it's important to know that you do not move this 2 at the beginning because the 2 is not attached to the 5. The 5 is its own separate entity. So first I need to break that 5 off. Then once it's broken off and I've got my n squared by itself, at that point in time I can move this. So your final answer is log base 6 of 5 plus 2 log base 6 of n. Alright, the next problem says use the change of base formula to evaluate log base 4 of 14. So what that means is I'm going to think back to my change of base. Remember, for change of base, we want our base down low. So I'm going to rewrite this as log 14 over log 4. I want my base down low. This I can put into my calculator. Remember though, when you enter it, you need to say log 14, close your parentheses, divided by log 4. When you do that, your calculator will spit out 1.904. Okay, now we're getting into solving. Oh, right. So this first problem, it says solve 4 to the 7x equals 63. I do not see any logs. This whole chapter has been about logs and e, and I don't see that here. So I'm going to insert log into both sides. So let me rewrite that for you. Log of 4 to 7x equals log 63. Now using my properties of exponents, I'm going to take this 7x and move it to the front. So I get 7x log 4 equals log 63. Now, in order to get x by itself, I need to divide by log 4 on both sides. On the left, it goes away, and I'm left with 7x equals, and on the right, when I put this into my calculator, I get 2.9886. But I need to take that and I need to divide by 7 in order to get x by itself. So I get x equals 0.4269. 0.4269. This next problem is solved a little bit differently. I have 2 logs on this side, but something that I see right away is that it's equal to 0. So I'm going to do something that's going to make this problem a lot easier for me to solve. I'm going to move this entire log over to the other side of the problem, to the other side of the equal sign. Because then when I do that, I end up with log 4x equals log of 5, which is a really easy problem because when we have a log on both sides, as long as they have the same base, and they do here because it's that invisible 10, then my log should just completely cancel out, and I can just say that 4x is equal to 5. Now to solve for x, all I have to do is divide by 4, and I get x equals 5/4, or 1.25. So this problem is a really, really easy problem as long as you recognize that you should move this log to the other side, allowing you to take these and just cancel the logs out, setting my arguments equal. Okay, so here is the first of those 3 problems we discussed in class. We hadn't really seen them, but I showed you that they're pretty quick problems to solve. Remember that if I have ln of e, they're inverse operations. They cancel each other out completely. So ln of e cancels, my answer is 5. ln of e cancels, my answer is 28. ln of e cancels, my answer is 6. Now for this next problem, and notice that I'm giving you some more practice problems too because we didn't really take a look at this stuff in class too much in detail. But what's important to know here is that yes, I do have ln of this thing equal to a number, but what's super important is that you know the base of ln is e. The base of ln is e. The base of ln is e. So now when you put it into exponential form, I have e to the 6th equals 5x plus 4. In the next problem, I have e to the 5th equals 5x plus 7. In the last problem, e to the 5th equals 2x plus 2. And then it's just a matter of doing calculations because we can ask our calculator what e to the 6th is, what e to the 5th is. So let's go ahead and put that in our calculator. I'll do one at a time. First one, e to the 6th is equal to 403. Holy cow. 403.4288 equals 5x plus 4. So to solve, I'm going to subtract 4, subtract 4. That gives me 399.4288 equals 5x. Divide by 5, divide by 5. And that gives me x equals 79.89. And I rounded to the nearest hundredth. So let's go ahead and do the next one. E to the 5th is equal to 148.4132 equals 5x plus 7. I'm going to subtract 7 from both sides, which gives me 141.4132 equals 5x. I'm going to divide by 5, which gets x by itself, so x equals 28.28. And the last one, the one that was actually on your study guide, e to the 5th we already said was 148.4132. That's equal to 2x plus 2. So I'm going to subtract 2 from that amount. 148.4132 minus 2. I get 146.4132 equals 2x. If I divide both sides by 2 to get x by itself, I get 73.2066 equals x. Okay, for this last set of problems that's new to us, the ones we didn't really discuss too much in class, I see that I have e to the x equals some number. Now, a few slides ago, 2 slides ago, we talked about how ln and e are inverse functions and that they cancel each other out. So what would be really convenient for us to do for these problems is to add an ln, because if we were to add ln, we can cancel out, let's move this a little bit, we can cancel out completely the ln and the e, leaving only x on the left and ln of 1/5 on the right. And then ln of 1/5, we just plug that into our calculator, and we get negative 1.609. For the second one, we add that ln in, it cancels on the left, and we're left with x equals ln of 5. Again, we plug that into our calculator. ln of 5 equals 1.609. And in the last example, ln, it cancels on the left. I have x equals ln of 3/4. When I put that in my calculator, I get negative 0.2877. All right, this last problem says, without graphing, determine whether the function represents exponential growth or exponential decay. Okay, so let's go over the rules. In exponential growth and exponential decay, the way we determine that is by looking at the base. I do not care about anything else, just this value that my exponent is on. And the rules are, if that number is greater than 1, I have growth. If that number is less than 1, I have decay. So in this example, I have 7/10. This number is less than 1. So I know that I have an exponential decay function. That's it. Good luck on your tests.